Welcome to New Findings of the Universe. Today, we are diving into a headline that sounds impossible at first. A planet that some people are already calling better than Earth. The world is called K218b. And the reason it exploded across the internet is not because of a spaceship or a mysterious signal in the night. It is because of chemistry, and because a telescope can read that chemistry using nothing but starlight. What was reported is that scientists detected atmospheric hints that could be connected to life. Not a confirmed discovery of life, but a signal strong enough to make the scientific world lean forward in their chairs and say, "We need to look again." K218b is far away, about 124 light-years from us, and yet in a very real sense it is close. Because for the first time, we are not just guessing what a distant planet might be like. We are measuring what is in its air. The excitement centers on a molecule called dimethyl sulfide, and in some discussions, a closely related sulfur compound. On Earth, dimethyl sulfide is strongly linked to biological activity in the ocean, especially microscopic marine life. It is also a fragile gas. It does not last long in an atmosphere, which means that if you find a lot of it somewhere, something must be making it again and again. That is the spark that lit this whole story. If K218b truly has large amounts of that gas, then one explanation could be a living ocean, a world wrapped in deep water with biology churning beneath a thick sky. But here is the key. K218b is not an Earth twin. It is bigger than Earth, heavier than Earth, and it belongs to a class of planets we do not have in our own solar system. Some scientists think it could be a water world under a hydrogen-rich atmosphere. Others argue it might be more like a small gas giant without a true surface. In this episode, we are going to walk through how this planet was found, how the James Webb Space Telescope reads an atmosphere across the darkness, why the sulfur signal caused such a reaction, and why careful scientists keep repeating one word: caution. Stay with me to the end. Because the most important part of the story is not just what may have been detected, it is what comes next. And if you want more episodes like this where the universe feels a little closer, subscribe to the channel because we follow the newest findings of the universe every week. The story of K218b did not begin with James Webb. It began with steady, patient surveys that watched thousands of stars for tiny dips in brightness. In the middle of that ocean of data, one particular star showed a repeating pattern, small regular dimming that suggested a planet was crossing in front of it. That is the transit method, a shadow so small that it feels unreal. Yet it can reveal a world. The planet was given the name K218b. And from the beginning, it stood out because it sits in a region around its star where temperatures could allow liquid water, depending on what its atmosphere is like. Then the follow-up work began, because in astronomy, every big claim is built on repeated checks. Scientists worked to confirm the orbit, to estimate the size, and to understand the star itself. The star is a cool red dwarf, smaller and dimmer than our Sun. That matters because a red dwarf changes the rules. Its habitable zone is much closer in, meaning a planet can receive Earth-like levels of energy while orbiting very near the star. That closeness is good for observation, because transits happen more often and the signal is easier to collect. But it also raises questions about stellar activity and how a close planet might hold on to an atmosphere over long periods of time. As years passed, space telescopes gathered more clues. Evidence pointed to an atmosphere that might include light gases. And in some analyses, there were hints consistent with water vapor. The conversation gradually shifted from, "Is there a planet?" to, "What kind of planet is it?" That is when K218b became more than a dot in a catalog. It became a target, a world that could teach us about a category of planets that may be common in the galaxy. When the James Webb Space Telescope entered the picture, it pushed the story into a new era. Webb can see in the infrared with extraordinary sensitivity, and that is where many molecules leave their fingerprints. Observations suggested gases like methane and carbon dioxide in the atmosphere, which fit with the idea of a thick atmosphere and a complex chemistry. Later, a team reported a signal that could match dimethyl sulfide, and the discussion around life became louder. Because dimethyl sulfide is not just any molecule, it is a molecule with a strong biological association on Earth. But the best scientific stories are never single moments. They are chains of evidence, debate, and verification. And that is exactly where we are now. To understand how a telescope can talk about chemistry on a planet we cannot see directly. Imagine listening to a song through a wall and trying to identify the instruments. You do not see the band, you do not see the room, but the sound carries clues. In astronomy, we do something similar with light. When K218b passes in front of its star, a tiny portion of the starlight passes through the planet atmosphere before it reaches us. That atmosphere absorbs specific wavelengths of light depending on what gases are present. What reaches the telescope is slightly changed, and those changes form a pattern. The James Webb Space Telescope measures that pattern as a spectrum, a detailed map of how much light arrives at different wavelengths. If a gas is present, it can carve out a subtle notch in that spectrum. Methane leaves notches in certain infrared regions. Carbon dioxide leaves notches in others. Water can do the same. When scientists say they detected a molecule, they mean they found a pattern in the spectrum that matches the known laboratory signature of that molecule, and that the match remains when they test different models of the atmosphere. But here is why this is so hard. Different molecules can overlap, meaning their signatures can resemble each other in certain ranges. Instruments also have quirks, and the data must be processed carefully to remove noise, correct calibration, and account for the star itself. If you make different choices in that processing, a weak signal can grow, shrink, or shift. That is not a flaw. It is the reality of measuring something incredibly small. We are not reading a billboard. We are reading a whisper. This is also why repeated observations matter. Webb has multiple instruments that can observe in different infrared ranges. If a claimed molecule appears in one range but not another, it can raise doubts. If it appears consistently across independent methods, confidence increases. That is why the story emphasized repeated scans, using different parts of the telescope, seeking the same chemical fingerprint from two angles. The miracle is that this method works at all. We are effectively reading the atmosphere of a planet across 124 light-years using the light of a star, turning physics into a language we can decode. That ability is the real revolution. Even if a specific molecule turns out to be less certain than early headlines suggested, the technique itself is opening a doorway. We are moving from imagining distant worlds to measuring them, and that shift changes everything about the search for life. Now we focus on the molecule at the center of the storm, dimethyl sulfide. On Earth, dimethyl sulfide is deeply connected to ocean biology. It is linked to microscopic life in the sea, and it can enter the atmosphere through processes related to marine ecosystems. That is why it is sometimes described as a potential biosignature. Not because it guarantees life, but because life is a strong explanation for its presence in our own world. Another reason scientists care is that dimethyl sulfide does not like to stick around. In an atmosphere exposed to radiation and chemistry, it tends to break down relatively quickly. That means a large amount of it would usually require an active source to keep replenishing it. So when researchers reported a possible detection of dimethyl sulfide in the atmosphere of K218b, it made people imagine a world where something is constantly producing it, perhaps biological activity in a global ocean. But caution is not just a boring word. It is the discipline that protects discovery from becoming a mistake. Compatible with dimethyl sulfide is not the same as confirmed dimethyl sulfide. A spectrum can sometimes be explained by more than one combination of gases, especially when the signal is weak. And a planet like K218b is not Earth. Its atmosphere could be rich in hydrogen. Its temperature and pressure could be far from what we know. Its chemistry could allow pathways that are rare here. A molecule that screams biology on Earth might have other origins in a very different environment. There is also the larger rule in astrobiology: one molecule is not enough. Life is a system, and proof usually requires a consistent set of signals that reinforce each other, along with a strong argument that non-biological explanations are unlikely. That requires knowledge of the planet's climate, its radiation environment, the structure of its atmosphere, and how its chemistry behaves over time. And even with Webb, we are still learning those details. So why is the story still so important? Because it is one of the strongest and most specific conversations we have ever had about possible biology beyond Earth based on atmospheric data. It is not a blurry photo. It is a measurable chemical question. Is this molecule present? If it is present, what is making it? Can we rule out non-biological sources? That is the path forward. And the beauty is that every new observation, every new analysis, either strengthens the case or teaches us how to do this better. And both outcomes push humanity closer to the answer we all want. Let's address the phrase, better than Earth. It is dramatic, but it can also mislead. K218b is not a second Earth with a familiar sky and a familiar ocean. It is larger than Earth, and it sits in a category of planets called sub-Neptune, meaning it may have a thick atmosphere and a very different internal structure. That kind of world could be uninhabitable in some scenarios, but it could also be habitable in ways we did not consider before. The key is not whether it is better. The key is whether it can support life at all. One idea that keeps appearing in discussions is the concept of a Hycean world, a planet with a deep global ocean and a hydrogen-rich atmosphere above it. If such a world has the right temperature range, it could allow microbial life, even if the surface conditions are not like Earth. This matters because sub-Neptune planets might be common in our galaxy. And if a portion of them have ocean layers with habitable zones, the number of potentially life-friendly worlds could be enormous. But there are serious questions. If the atmosphere is very thick, the pressure at the ocean surface could be crushing. If the planet receives the right amount of energy overall but traps heat efficiently, the ocean could be too hot. If the world is more like a mini gas giant, there may not be a stable liquid ocean surface at all. Some models allow a water-rich environment. Others suggest a very different nature. And because we cannot see the surface, we must infer everything from the light passing through the atmosphere. The star adds another layer. Red dwarfs can be active, producing flares that influence atmospheric chemistry. A planet close to a red dwarf may be affected by that activity across billions of years. Yet the same closeness makes the planet easier to observe by transits, and that is why we have such good data compared to many other exoplanets. It is a trade-off, the universe giving with one hand and taking with the other. So the most honest way to frame this world is not better than Earth, but fascinating. A planet in a promising temperature region, with a complex atmosphere, possibly water-rich, and possibly carrying a chemical hint that we associate with biology. It is a target that forces us to refine our definitions. Habitability is not a single picture. It is a spectrum of environments, and K218b sits right where that spectrum becomes truly interesting. Now we talk about confidence because a lot of the internet hears probability and thinks certainty. In science, confidence levels are tools that help us describe how strongly the data supports one interpretation over another. A result can be intriguing and still not be definitive. In many fields, the gold standard for a major discovery is extremely strict, because history has shown how easy it is for weak signals to masquerade as breakthroughs. In the K218b story, early discussions described a strong level of confidence for a potential detection. Yet the scientific community did what it always does when something is extraordinary. Other teams reanalyzed the same data. They tested different models. They tried alternative explanations. They looked for signs that the signal might depend on a specific assumption. Some analyses became more skeptical, suggesting that the evidence for dimethyl sulfide might not be as robust when everything is combined, or that other molecules and atmospheric structures could explain the same spectral features. This is not a scandal. It is science working in public. When an observation sits near the boundary of detectability, small differences in data processing can matter. The way you correct for instrument effects, the way you model the star, the molecular databases you use, the assumptions you make about atmospheric temperature and cloud layers. All of these can influence what molecule appears to fit best. The fact that the community is arguing is exactly what you want, because it means no one is allowed to declare victory without surviving the strongest criticism. What remains true is that K218b has become one of the most important test cases for exoplanet atmosphere science. Even the debate itself is pushing the field forward. It is teaching us what kinds of measurements are needed to separate similar molecules. It is teaching us how to design future observations to reduce ambiguity. It is showing us the limits of current instruments and the ways to get around those limits through repetition and independent confirmation. So where does that leave the life question? It leaves it open, but no longer in the realm of pure speculation. We now have a specific target, a specific set of molecules, and a specific plan. Observe more, analyze better, and demand stronger confirmation before using the word life. That may sound slower than the headlines, but it is the only way a discovery becomes real. And when it becomes real, it will stand like a monument that no one can easily knock down. Now, let's do something careful but imaginative. Imagine that future observations confirm the presence of a sulfur compound like dimethyl sulfide in the atmosphere of K218b with much stronger certainty. And imagine that scientists can convincingly argue that non-biological production is unlikely in that environment. What would life there probably look like? The most likely answer is simple life, microbes, not forests. Not animals, not civilizations, but microscopic organisms living in water, using chemistry as fuel. On Earth, life began small, and much of Earth life is still microbial. Microbes thrive in extreme environments, including deep oceans where sunlight never reaches. Some ecosystems rely on chemical energy from hydrothermal vents, where hot, mineral-rich water meets cold ocean water, creating gradients that biology can exploit. If K218b has a deep ocean and internal heat, it could potentially host similar chemical engines. Not identical, because the atmosphere and pressure could be very different, but analogous in the sense that life could use chemistry rather than sunlight. If the atmosphere is hydrogen-rich, that changes the chemical landscape. Hydrogen can be a powerful player in atmospheric reactions, and it can influence what molecules form and how stable they are. It could also affect how easily certain gases escape into space. A biosphere in such a setting might produce byproducts that look unusual to us, or it might produce familiar compounds in unfamiliar ratios. That is why biosignatures are not just about detecting a molecule, they are about detecting a story. A chemical imbalance that persists because something is actively maintaining it. But we must hold on to humility. We do not know if the planet truly has an ocean surface. We do not know if clouds and hazes hide layers that change the spectrum. We do not know the exact temperature profile of the atmosphere. We do not know whether the pressures are too extreme for stable biology. And we do not know whether the signal points to one exact molecule or a blend of several. Still, the reason this matters is psychological as well as scientific. K218b reminds us that the search for life is not limited to the nearest rocks. It is a search across chemistry, across light, across patterns. It is a search that asks whether life is a rare miracle or a common outcome. And even before we have the final answer, we are already learning that the universe is more readable than we once thought. And that is a powerful step toward the day when we can finally say, with confidence, we are not alone. So what is the real takeaway from the James Webb story? It is not that we have found a perfect new Earth. It is that we have entered an era where we can test the idea of life beyond our solar system using measurable atmospheric evidence. We can point a telescope at a distant star, watch a planet cross, capture the altered starlight, and decode the fingerprints of molecules in that planet's sky. That is a capability humanity did not have a short time ago, and now it is real. K218b sits at the center of this moment because it is a rare combination. A planet in a temperature range that keeps water on the table as a possibility. A world that transits often enough to be studied repeatedly. A target that appears to have a complex atmosphere. And a reported hint of a molecule that, on Earth, has a strong link to ocean biology. Those ingredients are enough to make headlines, but they are also enough to make serious scientists slow down. Because extraordinary claims demand extraordinary evidence. As the debate continues, it is worth remembering that uncertainty is not weakness. Uncertainty is a map of what we still need to learn. Every reanalysis, every skeptical paper, every alternative model helps refine the question. It forces the field to improve methods. It motivates new observations designed to break the tie between competing explanations. And whether the sulfur signal strengthens or fades, the outcome will still move the science forward. If it strengthens, we may be approaching the first solid evidence of biology beyond Earth. If it fades, we'll still have a clearer understanding of a fascinating sub-Neptune world and a better strategy for the next candidate. The universe rarely hands us simple answers, but it does offer us moments where the door cracks open. K218b is one of those moments. A distant world, invisible to our eyes, leaving a tiny signature in the light of its star. And a species on a small blue planet learning how to read that signature like a message from across an ocean of space. If you want to keep following these breakthroughs with me, subscribe to New Findings of the Universe. Because the next discovery could be closer than we think, and when it arrives, you will want to be here to hear the story from the beginning.